A power system is basically anything that functionally delivers electrical power to the plant or the factory, and then that is used to drive the plant. In other words, drive a process, drive a machines, whatever it has to do. But the idea is that in traditional supply of electricity, there's a couple of terms that we need to talk about, and that is the term the grid, and the grid is basically the electricity is supplied from a local or a national authority. And they have several stages of power generation. We'll talk about each one, but they deliver the power from their source, convert that into electrical energy, and then deliver that to the pin. So the most common way of the grid, or the common waveform that the grid actually adopts, is the AC, or alternating current, and itself is sorry, can I watch this later? Yes, we will be recording it. Yes, definitely. So it is available for review at a later stage, and that is available to everyone, by the way. So the idea is that we go through and use the AC waveform, and the main reason for that is that when it is required to deliver energy over long distances, then it is able to be transformed into higher voltages, reduced current, and thereby reducing the losses in the system. Okay, so the waveform that is being used as a reference is what is referred to as a sine wave, and the sine wave has a couple of characteristics. The main being a magnitude, and the other one being the frequency. So the frequency is what can be determined, and the voltage or the magnitude is worked out a certain way as well. Okay, so the what you see when you generate an AC waveform is typically what you see here, and this is seen as a single phase AC waveform. In over many years of optimization, the three-phase machines have become the more prevalent one, and definitely are the ones that are prevalent in generation of electricity. So hence the electricity is shown to be the three that you see here, and these are three waveforms which are available to be used as power by the load. Okay, and and a couple of things is they do, I guess you can see, they do have magnitude, in other words a peak-to-peak magnitude that you can see here, and a frequency. So it's the frequency between the different troughs. Okay, and you can see three interposed waveforms onto this one because of the generations. Now, these are not put onto the same cable. They are three separate cables that carry these, but they are generated from the same machine. Okay, so three-phase power is the one that is usually been adopted, and is the one you'll probably have on site as well. So that there are one of the things. Okay, so they do have through standardization a great deal of adoption through most of the industries, and in fact all industry and most consumers around the world. Okay, so the way to measure And to use those units, electrical energy is in two ways. Firstly, as power, which is able to be delivered and have effective work, is a cross product of the voltage and the current, okay, measured in watts. And also, if we deliver that power over a period of time and constantly give it that thing, then we create the energy that the system is delivering, and that is basically the power times the time, and that is referred to as the watt hours. Okay, when you build your electricity from a grid, from the grid utility, usually is within watt hours. Okay, so there is another way to measure the waveform and convert that into a calculation value, and that is if we use what is referred to as the root mean squared. And it is a value which is equivalent to a DC value of the power that goes into it. So it actually gives you an energy that can be used by the load. Okay, and the equations that are typically given and are used in calculations is the power is equal to the voltage times the current. Okay, fairly simple. And if we look at a waveform of a sine wave, and we note that it has a peak-to-peak magnitude, then that term root mean squared, which is the effective energy value from the effective DC value from the sinusoid, it can be derived based upon a pure sinusoid, that the V peak to peak divided by √2 is equal to the RMS. And that's purely based upon some physics and an understanding of the thing. So they're both also applicable to both AC waveforms, both current and voltage. So what you see, if you put an oscilloscope, which is a waveform displaying machine, and look at the waveform that you see, the voltage could be represented in blue, the current in red, the current in blue, and the cross product of it, which is the power, can be represented in pink. So you may also note that both the voltage and current are symmetrical around the zero axis, which they are, but as soon as you cross multiply them, then it becomes a positive power. So that is a typical feature that you will see, and it means that there is power being delivered to the actual the load, okay, and it is in a positive direction. So now what occurs is, depending upon the load, there may be a phase shift between the voltage and the current, and I'll just very quickly go through that. If the load was purely resistive, in other words, it had no ability to store energy, then the current and voltage would be aligned, just as you see in this way, so that the voltages and the current have exactly the same crossing points and the same values where they actually become a minimum maximum. Now, when we put in an element that can store energy, such as an inductor or a capacitor, then the current will be displaced from the voltage, and the load will have that effect. Now, what it does in a lot of the times is that reduces the efficiency of the delivery of the power, and by having noticing the phase, the angle between the voltage and the current, you can then derive some other figures, and the figures are derived in the type of power that is being delivered. So this is a mistake, it actually should be Q. So that the power, which is useful power which can be delivered to the load through resistive is what you see here. Okay, the one that is component which is used in the storage of the element or the storage of the energy within the capacitor or within the inductor is what you see here. And it cannot generally be used for delivery of power. So it is wasted energy as far as the load is concerned, and also as far as the transmission is concerned. So that when we look at the ratio between the two, that is referred to the power factor, okay, and the equation and the actual value which needs to be, or the actual power that needs to be delivered to supply that type of load is what you see here. Okay, and there are definitions, and the very quick definition, this is referred to as the active or real power, this is the reactive power, and this is what is referred to as the apparent power. Okay, so and looking at that equation again, we know that the apparent power, as I mentioned before, is simply the cross product of the voltage and current. The active power, which is the one that can be delivered and do useful work, is what you see here. And the reactive power, which can be thought to be of wastage or a element that needs to be used, is what you see here. And depending upon the supply and various other points, you may or may not be charged extra because your load may be generating these. Okay, so when we look at the delivery of the process, we note that there could be very large infrastructure from a generation or generation equipment into a transmission equipment, and these could be over many, many kilometers, into distribution. And this is the second part we refer to as the transmission. Okay. Now the next part, which is the step after the transmission side, is what is referred to as distribution, and it generally occurs at now the generation of electricity under coal fire or turbine driven generation is roughly around about between the 11 kV and the 30 kV voltage level. That's coming straight off a generator. The generator then gets the voltages then gets transformed higher to allow the transmission over greater distances. Then once it gets closer to the point of where it needs to be used by the consumer, it is stepped down and then becomes a distribution level. Okay, and they're typically at 33 kV and less. And it then gets to another series of step down transformations, which then can be displayed or delivered to the end user. Okay, so the typical and most prevalent one around the world of this type of system is referred to as a three-phase network, and a lot of higher current, a lot of utilities a lot of loads use the three-phase network, and it is used throughout the network. When we and is there to make sure that you do have a higher amount of current that can be delivered to the customer rather than just a single phase unit. Okay, so from the generation part right down to into the consumer, there are various steps and various componentry that control the various steps in between it, and that is referred to as distribution equipment, including things like transformers, current control devices such as circuit breakers, control gear, and obviously the cable. So the points or areas where you are able to either have a control of the power, or you need to be able to transform it up and down, is referred to as substations. And these are quite common in the whole of the utility network. And they usually include, as I said before, transformers, some type of control equipment, and switches or switch gear, and that's the common term, is switch gear, that will actually be able to either isolate or function or close the current through the particular circuitry that it's attached to. Okay, and there are several types, both indoor and outdoor, and it depends upon where they're located as to what type they are used. Okay, so what is typically of an outdoor is what you see here in the transmission substation, and right down to a indoor distribution center, say something within a large building or a factory complex. So in the higher voltages, which is the ones that after the first transformer from a generator, is what you see here, the high voltages designed for long distance distribution of the energy. Okay,